Right, let's look at question 5. This is the inclined plane question to do with work, energy, and power. So we have a box of mass 60 kilograms, and it starts from rest. So that is an indication that the initial velocity is 0 at a height h, and slides down a rough slope. Once again, that tells us that there are some frictional forces at play here. A length of 10 meters, that's our delta x, our displacement, makes an angle of 25 degrees with the horizontal, and it undergoes a constant acceleration of 2 meters per second squared. So that constant acceleration tells us that we have some net force acting during that time. Alright, the first question, state the work energy theorem in words. This you really just need to learn off by heart. It should be word perfect. The net work done on an object, be careful, sometimes people say by an object. It's not the object that's doing the work. The work's done on the object by a force. So the net work done on an object by a net force is equal to the change in kinetic energy of the object. Right, 5.2 asks for a free body diagram, and that's asking for a very particular type of diagram, a free body diagram, where the forces are shown emanating from the center of mass, which we indicate with a dot. Before we answer the question, let's just consider the forces. Firstly, notice that there is no applied force in the situation. There's no engine driving this box. It is simply a box that slides down the slope due to its weight, or the force of gravity. So there's no applied force, so don't put in F app. That would only be if we had a car driving up or down a slope, or some other vehicle, or any object with a driving force, but there's no applied force here. So what forces do we have? Well, we've got the weight of the object, the force due to gravity that acts straight down. Because it's a bumpy surface, we have a frictional force that retards the motion, and then because it's on a surface, we have a normal force at 90 degrees. So let's now draw our free body diagram. Force due to gravity acts straight down. Make sure you use a ruler, please. Straight line acting vertically downwards. Force due to friction acts up the slope, so that line would be drawn in parallel to the slope. And then the normal force acts at 90 degrees. Now just try and get your forces in the correct kind of ratio. The normal force is balanced by the perpendicular component of the force due to gravity, so make sure those are approximately equal. The force due to friction needs to be smaller than the parallel component of Fg. Mine might be a little bit long, but it doesn't have to be exact, but a consideration of proportion is a good idea. All right, 5.3. The box reaches the bottom of the slope. Calculate the kinetic energy using equations of motion. So you can't use an energy calculation. You must use equations of motion. So we'll use Vf squared equals Vi squared plus 2a delta x, where delta x is the displacement down the slope. Vi is 0 because it starts from rest. We are told that the acceleration down the slope is 2 meters per second squared, and that the displacement delta x is 10. So our Vf squared is 40. Now you can square root that to get Vf, but we know when we use our kinetic energy formula we're going to need V squared. So it's perfectly sensible to leave that as 40. Ek is a half mv squared. The mass of the box is 60. And V squared now we have from the calculation above is 40. So we can just put 40 in place of V squared. That gives us our kinetic energy of 1,200 joules. Right, 5.3.2, the work done on the box by the gravitational force. We need to be careful here. We're looking for work done, and it's just by the gravitational force. Remember, there were 3 forces that we indicated in our free body diagram, and this question focuses on just one of those forces. Now, if we draw that force in, I've drawn it in blue there, that's the force due to gravity, the gravitational force. Now, remember that that force is made up of 2 components. The component perpendicular to the plane, we indicate there Fg perpendicular, and then the components parallel to the plane, Fg parallel, and it's that component that does the work, because the box only moves in that direction. And so it might be helpful to redraw that component over there. It's the same length, same direction, so we haven't changed the force. But then to also remember that Fg perpendicular is balanced by the normal force, and so there's no work done by that component. Now, there are two ways to answer this question. I'm going to start by answering it in terms of taking the force due to gravity Fg and ignoring all the other bits and pieces. So let's get rid of that, and we'll focus just on Fg, the force due to gravity. So the force due to gravity is equal to mg, mass times gravity, and delta x is the displacement, and then in the diagram there, delta x, notice, is the 10 meters, and the theta then for cos theta is the angle between the force and the displacement. So I've redrawn Fg in red just to highlight it. The displacement is given there, so theta then is the angle that I've indicated there between Fg and the displacement delta x. So it's not 25, it's 90 minus 25, and so if we add in the values, m is 60, g is 9.8, delta x is 10, and the theta then is 90 minus 25, or 65. If you multiply that out, you get work done of 2485 joules. Now there's another way to do this, and that's to consider that it's only the parallel component that does work. And so if we get rid of all of that and we draw in our parallel component and our displacement delta x, and then we work with that, our parallel component is given by mg sine theta, and that theta is the 25 degrees, delta x is 10, and now because we're only considering Fg parallel, the angle between the parallel component and the displacement is 0, and that's why we have the cos of 0, and that obviously gives us the same answer. So either of those two methods would have been fine. Right, 533. Work done on the box by the frictional force using the work energy theorem. Now when they give you that proviso, you have to start with the work energy theorem, W net equals change in kinetic energy delta Ek. Now in this case, the net work is the sum of all the works, and so those are the forces doing work, the force due to gravity, and the work done by the force due to friction. So the work done due to gravity and the work done due to friction. There's no work done by the normal force because there's no movement in that direction. Delta Ek is final kinetic energy minus initial kinetic energy. Now work done due to gravity we've just calculated, it's 2485. Work done due to friction is what the question's asking us. The final kinetic energy we've just calculated earlier is 1200 joules, and the initial kinetic energy is 0 because it started from rest. So if we solve for work done due to friction, it's minus 1285. Wherever you get a negative sign, you do need to interpret that sign, and in this case that means that the work is done up the slope or in the opposite direction to motion, which is obviously down the slope. And then finally, the magnitude of the frictional force, well, the work done due to friction is equal to F delta x cos theta, where F is the frictional force. We've just worked out the work done is minus 1285, and that equals the force due to friction times delta x, which is 10, times by the cos of theta, where theta is the angle between the force and the displacement. Remember, the frictional force acts up the slope, and delta x, the displacement, is down the slope, and so the angle between those is 180, which is where we get that cos of 180 from. And if we solve for the frictional force, then it's 128.5 newtons.